Hi. In this video we're going to look at forces. In particular we're going to look at the frictional force. So let's start with an example. I'm going to draw a box. It's going to be a heavy box and it's going to exist on a flat surface. Okay, so the surface is meant to be flat and I'm going to push the box in a certain direction. So I'm going to push it this way. When I'm pushing it, I'm applying a force to it. But because the box is really heavy, the box isn't actually going to move. It's going to be stationary. But from what we've covered so far, this doesn't make any sense, right? Because if I'm applying some force to it in a direction, the forces on this box as I've drawn it are imbalanced. So it should be moving, or it should be accelerating in this direction. So there's something going on here that we haven't covered yet, and that is the frictional force. The frictional force is based on how sort of heavy the object is and how rough the surface between the box and the ground is. So obviously if I have a 200 kilogram weight, it's going to be harder to get to move than it is like a 10 kilogram weight, right? So let's draw in some forces here. We've got a gravitational force acting on the box. This force of gravity is going to be 9.8 times 200. We've also got a force that resists the movement into the ground. That's called the normal force. So that's coming up. We'll call that the normal force, which is going to be opposite to the force of gravity. It's the only other thing acting in the y direction in this example. And because it's not accelerating down or up, it must be the exact same amount. Okay, so we need a force that's acting in the opposite direction for this box to be in equilibrium, for it not to move, right? And this is going to be our frictional force. We're going to call it the force of static friction, SF for static friction here. And what that force does is it opposes the force that you're pushing onto the box. This force of static friction, as we said, it relates to the weight of it. The heavier it is, the harder it's going to be to get in motion to start with. And it also relates to how sort of the roughness of the ground compared to the box. So this force of static friction turns out to be less than or equal to, and I've drawn that the wrong way, less than or equal to some frictional coefficient, we'll call it SF here, and the normal force, which is this guy up here. So this is what the static friction is. It's related to the normal force, which again is related to how heavy the object is. And it's related to this sort of roughness factor, which we call the coefficient of static friction. There's also another type of friction, which is dynamic friction. That friction only works when the object is in motion. So we can call that the force of dynamic friction, and that equals a different coefficient. It's normally less than the one above it. It's normally less than the static friction. And it's also multiplied by the normal force. Now, we're not going to consider this one so much in this course, but I'll sort of discuss it with you now so you can get an intuitive feel for what's going on with this box. Okay, so let's have a look at this applied force here and how that's going to affect whether this 200 kilogram block moves forward or not. So we have the force that we're applying. We have the frictional force of static friction. We have a dynamic frictional force. And we have the net force on the box. We'll call that net. So let's apply different forces. We're going to push it to a different amount and different force that we're applying. And we're going to see what happens to the net force on the box. So if we were applying 100 newtons of force, so this is going to equal 100 newtons in our first example, and we want to know what's happening to the box. Well, first we have to work out what the static frictional force is up here. So we need to know what this value is, and I'll just write down an example here. Let's let it equal 0.5. So if the coefficient of friction, of static friction, is 0.5, we can work out what this static frictional force is. So the static frictional force will be less than or equal to 0.5 times the normal force, which is 1960. So the static frictional force will be less than or equal to 980 newtons. Okay, so we've applied 100 newtons down here. What's the static force going to be, the static frictional force? Well, in this case, it's not going to be 980 newtons, because if it was, and I'll draw a little picture in here, if we're applying 100 newtons this way, and there's a force that's 980 newtons this way, that means the frictional force is going to move the box in this direction, right? Because there's a force imbalance. That's 880 newtons. That doesn't make sense in real life, right? If I'm trying to push a box one way, it's not going to suddenly move the other direction if I'm not pushing hard enough. So this is not how the frictional force works. What this static frictional force does is it opposes the applied force up until we get to 980 newtons. So if I apply 100 newtons to the box, the static frictional force will also be 100 newtons. There will be no friction from dynamic friction because the box isn't moving. So the net force will be 0. The box will not move at all because we're not pushing hard enough to overcome this frictional force. If I was to apply 900 newtons, the same thing would happen. We'd have a static frictional force of 900 newtons. No dynamic frictional force, and our net force would be 0. If we had exactly 980 newtons of force, we would have exactly 980 newtons of static friction. If we had slightly over 980 newtons, then the box is going to start to move, right? Because we've overcome this static frictional force. When the box is moving, the static frictional force isn't available anymore. We start using this dynamic frictional force. So normally that's less than the static frictional force, so we'll say it's equal to 0.2. So the dynamic frictional force is going to be 0.2 times the normal force, 1960. Do I have a calculator here? So we're going to get a dynamic frictional force of 392 newtons. So the static friction is going to be 0. This is going to be 392. And it's going to occur in the opposite direction to which we're pushing. So it's going to be 392 newtons. The force we're applying is 981 newtons. So the net force is going to be 981 minus 392. And we get 589 newtons of force. So you can see that we're pushing, nothing's happening. Then eventually we break the static friction threshold. Once we get over that, the dynamic frictional force comes in and the box starts moving. Okay. Now, in this unit, we're not going to cover too much into dynamic friction. We're going to be largely concerned about whether a box is moving or not. So we're going to be looking at the static friction. So we'll look a little bit more into that. The way that they come up with this, or the way that you can visualize they come up with this coefficient of static friction, is that they get this box and they keep applying a force to it more and more and more and more and more, and then they see when it moves. So if we rearrange this equation, we get the static friction coefficient is the force of static friction divided by the normal force. So this, I'm using an equal sign because this is right at the point that the box starts moving. Now we know the normal force because we know how heavy the box is. So we know this. We also know the static friction force because we know how much force we're applying. So if you can measure the weight of the object and you can measure how much force you're applying to it right at the point that it starts moving, you can work out this coefficient of static friction. So that's the coefficient of static friction. When we use this equation here, again, we're just going to be concerned if the object is moving or not. So we're going to use the frictional force. We're not worried about static friction here because we're only looking at static friction. So I'll call it the frictional force equals the coefficient of friction times the normal force. And this is the equation we're going to be using to determine if a box is moving, if it's not moving, or if we want to work out what the coefficient of friction is, depending on the question. So let's have a look at a question. So we've got a person pushes a 10 kilogram box down the road with a coefficient of friction of 0.25. Determine the force the person must exert to move the box. And when we're talking about this, if it's not otherwise stated, we're talking about a horizontal force that we're applying to the box. So let's draw a diagram. Got here, we've got a flat surface. Okay, a person pushes 10 kilogram box, so we've got our gravity force. 9.8 times 10. Got 98 newtons. We're pushing the box this way. We've also got a normal force, which is opposite to the gravitational force, 98 newtons. And we've got a frictional force that's coming out the other way. So frictional force, and we've got an applied force coming this way. So what are we looking at? Determine the force the person must exert to move the box. So they got to push harder and harder and harder until they overcome the frictional force. So we need to work out what the frictional force is. When we work out that, that's how hard they're going to need to push it, plus a tiny bit more to be able to move that box. So the frictional force is mu times the normal force, which is 0.25 times 98 newtons, which equals a quarter of 98, is 24.5 newtons. So the person would have to apply 24.5 newtons to be able to move the box. Okay, and that's our answer. So force equals, if we wanted to show this fully written out, at the point of motion, we've got a net force of 0, but it's just slightly more than 0. That equals the force plus the frictional force. So the force equals negative frictional force, which equals, so that's 24.5 newtons in this direction, in the negative I direction. We can call that negative 24.50. So that means our force is going to be 24.50 in the positive I direction. So that's how much force we're going to have to apply to just start it to move. Okay, let's look at question 3. So Jane holds a rope that is attached to a 200 kilogram block that is at rest on the floor. So we've got block, it's 200 kilograms, the floor is flat. We've got a gravitational force that's being applied to it, and that force is going to be 9.8 times 200, 1960 newtons. Okay. She pulls at an angle of elevation of 5 degrees. So she's got a rope, she's pulling up on the rope, angle of 5 degrees. The block starts to move when he applies a force of 450 newtons. I think Jane is a girl, so I'm going to make it a she. Applies a force of 450 newtons. So again, in this case, it doesn't matter what direction we draw the rope, because we're just looking at the magnitudes of forces for this. So we've got, that's 5 degrees. The force being applied is 450 newtons. We've also got a normal force in here, just coming straight up. That normal force is going to be 1960. So when we apply the 450 newtons of force, or when Jane does, the block is just going to start moving, which means there's also a frictional force that's opposing the motion. So our frictional force is going this way. Determine the coefficient of friction between the block and the floor. So what's happening is we're pulling this way. The block is sticking to the floor. We're not going to pull it up in the air. If it was pulled up in the air, there'd no longer be a frictional force. So the force that we're applying in this direction is going to be the horizontal component. The frictional force is going to oppose the horizontal component of the force that we're applying. So we're going to equate those two, because right at the point of motion, this force, this horizontal force here, is going to equal the frictional force. It's just going to get over the top of the frictional force. So we're going to say that the force in the horizontal direction equals the frictional force. So we've got 450 cos 5 degrees. Now in this case, I don't have to worry about the 175 degrees from the positive x-axis, because I'm only concerned about the magnitude of this force, because it's going to be directly opposing the magnitude of this force here. That's going to equal my frictional force. We get a frictional force of 448.29 newtons. So that's my frictional force. We've also got a normal force, so using those two, we can work out our coefficient of friction. So we've got the frictional force equals coefficient of friction times the normal force. Coefficient of friction is frictional force divided by normal force. Frictional force 448.29 divided by 1960. And we get a coefficient of friction of 0.229. Okay, so that is an introduction to static frictional forces. We didn't look too much at dynamic frictional forces because we're not covering it so much, but that's how static frictional forces play a role in our force diagrams and our force calculations. So I hope you enjoyed the video, and I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.